Okay, so in this video, we want to consider a final class of special cases of L'Hopital's rule. If you consider a limit, in the case that it is yielding, you may see any of these three cases. So 1 to the infinity, infinity to the 0, 0 to the 0. All of these are indeterminate cases, and they can all be solved the same way, by not finding the limit directly, but finding the ln of the limit instead. We'll consider an example of this type right now, but the other two types are attacked in the exact same way. Take the ln of the limit, transform, so you can get a case where you can use L'Hopital's rule, and then you're good to go. So here our example. We will consider the limit, I'll call this L, as x approaches 0 from the positive side, and we'll take 1 plus the ln of 3x plus 1, and the whole expression to the power of 1 over x. So we have our base and we have our exponent. Well, as x goes to 0, 3x goes to 0, so we're left with ln of 1, which is also 0. So the base approaches 1, and the exponent, as x goes to 0 from the positive side, 1 over x goes to positive infinity. Now the idea is, if we stick with this limit directly, we can't solve this. But if we take the ln of the limit, then it's a different story. So we won't solve for L directly, but the ln of L. By continuity, you can interchange the limit and the ln, so the ln of the limit will be the limit of the ln of the expression. And now we can use properties of logarithmic functions. We can pull the exponent up front as a multiple of ln, but of course if you multiply by 1 over x, same as dividing by x. And now we can ask, what is the case of this limit? Well, as we said before, as x goes to 0, 3x goes to 0. This leaves us with ln of 1, which is 0. Therefore, ln of 1, which is also 0. Over, and clearly here, as x goes to 0, x goes to 0. So as we said, by taking the ln of the limit and rearranging a little bit, now we can use L'Hopital's rule. So we differentiate our numerator first. The derivative of ln, being the outside function, we're applying the chain rule here, is 1 over the argument. So 1 over 1 plus the ln of 3x plus 1 times, by the chain rule, the derivative of the argument, the derivative of ln of 1 is 0, plus the derivative of ln again is 1 over the argument. But we're not done. This is just the derivative of the ln. There's still the 3x plus 1 left over. Chain rule again, times the derivative of the argument, which is simply 3. Over the derivative of the denominator. The great thing here is the derivative of x is 1. So I'm not going to write all over 1, because it's just the expression itself. And if you notice, we have now a trivial limit. As x goes to 0, 3x goes to 0. So this term right here approaches 1 over 0 plus 1, which is 1. So the whole expression approaches 1. Now here again, 3x goes to 0. Therefore, this will approach ln of 1, which is also 0. So this approaches 0. So 1 over 1 plus 0 again will be approaching 1. So in the end, we have this term times 3. This approaches 1. This approaches 1, this is 3. So we have 1 times 1 times 3, so of course it's just 3. And here's where you have to be careful. This is not the final answer. We were asking to find the limit, that is L, and what we have found instead is the ln of L being 3. So how do we then solve back for L? Well, to solve for the limit, the original limit, we have to cancel the natural logarithmic function. And of course, this is done using the inverse being the natural exponential function. And the idea again is very simple. If a equals b, you can exponentiate both sides, and the equality is preserved, right? If a equals b, replace a by b, and you have the same equality. So let's exponentiate both sides. So the exponential of ln of L, replace ln of L by 3, is the same as the exponential of 3. But the natural exponential function is by definition the inverse of the natural logarithmic function. So they cancel each other out. And that leaves us with the original limit being e to the 3. And that's it. So always remember, if you have a 1 to the infinity, infinity to the 0, 0 to the 0 case, by taking the ln of the limit and tweaking the expression, you will have either a 0 over 0 or infinity case. You can apply L'Hopital's rule to arrive at a given answer, but this is not the original limit, but the ln of it. So to go back to L and not the ln of L, exponentiate your answer with the natural base that is e. And that's it.